when you put it in percent.
So I send those on the courier.
Okay. Oh.
Pump her.
Yeah, we have to. It's all cut off.
Yeah, we have to. Steams.
So no, that's not.
I already finished.
Let's say about the background. Yep. We saw it too late.
I sent it like 2 weeks ago. Oh, no, 1 week ago.
Yep. We saw it too late.
We saw it today morning.
Okay, let's go.
Okay, great.
I get in with you.
Water, yeah, this is a nice idea to have water here.
Yes.
20 minutes is a long time.
So you can take the mic in your hand, you know, also, but don't use it to point at things.
Okay.
You have a laser pointer here if you want.
How does it work?
Otherwise, you can have a laser pointer here too.
Yeah, exactly. And you can zoom in on things with that one.
All right.
Which button is the laser?
It's too advanced.
That one.
But the problem with the laser, if you turn this way, nobody will hear you.
No,
what you are saying.
exactly.
So that's why this is a better laser.
And you can,
Can't
unless you
point.
do it like this, you take the microphone and then put it here.
Oops.
How do you point on things?
If you click on this one,
Yeah.
the first one, so you can point it now.
Cool. And here you
Otherwise-
modify
Yeah.
here.
All right. Yeah. Good luck, guys.
Thank you. Hello? You want to raise that a bit? It's a bit low for both of us.
Just take it in my hand.
This. No? We will stand here.
Keep it on the ship.
Yes.
Ready?
May I please ask you to take your seats again?
I'm just waiting for the rest to sit, to have their seats. So, hello, and thank you for being here today for our presentation for the project AutoBike project. So, I am Elias. My name is Elias. I'm the team leader for the software team leader of the project, and here are our team. I hope you can read the names and see the faces. Pontus Lindum is the hardware team leader and GitHub manager. Tony, I always forgot your name. Mugisha is the hardware engineer and also safety manager. My colleague here, Linus, who is the hardware engineer and also responsible for LaTeX. Me, Mohamed Elias, I'm the software team leader and communication also responsible. And Joachim Nederlander, who is the software engineer, hello. And Pontus Gustafsson, also a software engineer. Here, a brief, or let's say the content, what it's about in our presentation. We will start with an introduction. We jump to the background. Then my colleague will take the method and results, and then we conclude. So, sorry. You may ask, what is AutoBike? AutoBike is a project that aims to build an autonomous, self-balancing bicycle. A bicycle that has the ability to ride by itself and simulate, in a way, the behavior of a human who rides a bike on the roads. As a background, we want to see what's the purpose of this project. In fact, the purpose of this project is not the bicycle itself, but rather the use of this autonomous bicycle for traffic safety tests. In fact, our sponsors that you cannot read here, unfortunately, who are Volvo Cars, Autoliv, Veoneer, Asta Zero, and Cycle Europe, who are our sponsors, already started. I'll play the video. Sorry. I apologize, but I have a video that should play here. No. It was working correctly.
Skip it.
Well, actually, I have to.
Just skip it.
Okay. So unfortunately, the video, I have plenty of videos here, but I'll check how to work. Our sponsors have their own, already have started having these safety tests in order to improve the object detection algorithm for autonomous cars, where the tested object, which is a human being or a bicycle, let me give it one more try. Sorry.
No?
No.
We have time. We have time.
The video started in the beginning and then it disappeared. Amazing. Can you just try? Oh, it's frozen. No presentation mode, maybe? Frozen. No. Here. Wait, don't click. No?
No,
This
that's a slideshow.
Okay. This is the one was started.
But let me try here, because I really want it. We apologize for the videos, I'll play them like this. I hope you can see them. So the object was following a straight line. However, with AutoBike, the bicycle can move freely in different directions or a non-line path. So this will simulate better the behavior of a human being who rides a bicycle. Back to the presentation mode. Please. Yeah. So a number of previous autonomous bicycles have been created over the few past years, and many of them are operational, where their design has been improved continuously through the past years. And this here behind me, the green bike, I don't know if you see well the colors. This green bike is actually the most recent bicycle that has been implemented and as a collaboration between Chalmers and Millarden universities. However, the increasing number of e-scooters and riders of e-scooters in the roads has given the motivation to our sponsors to expand these tests and include the e-scooters for safety, for traffic safety tests. So it became really a necessity, even for autonomous cars, to detect the e-scooters and behave conveniently. So in order to understand, or wanting to understand, let me play the video again. No, okay. Sorry, it will take them. Okay, there was a video here where we wanted to understand how the bicycle will balance. We wanted to understand the basic of the dynamics. Actually, a silly question here is why, when we push a bicycle without a rider, it can maintain its balance for, let's say, a good distance. Actually, it is the momentum that gives it the ability to maintain its balance. And whenever this ability is neutralized by the gravity, it will fall. There are two parameters here, which are the lean angle. I want to show them here. In fact, whenever the bike or the bicycle will lean to a certain direction, the steering, which is, I will rather point it here, the steering that you can see here will follow. So whenever the bicycle will turn to the right, the steering will turn to the right. Whenever the bicycle turns to the left, it will also follow, but until a certain degree that it will not be able to maintain its balance. And whenever the speed, the momentum that it has is neutralized, it will not maintain its balance. So there is another video here. Actually, it has the same idea, but which is in simulation to the e-scooters. Also, whenever the e-scooter will lean, as you can see in the angle on the left, in your right picture, whenever it will lean to the right, the steering will follow in order to try to maintain its balance. And from here, actually, we have the system of this project. So two parameters mainly: a lean angle as an input and a steering angle as an output. We want to control the balancing dynamics of the bicycle via these two parameters. So we started our project with meetings with our stakeholder, Mr. Jonas, who gave us the goals, directions, and also the requirements of this project. So mainly the goals are to design and build a prototype of a self-balancing e-scooter that matches the features and functionalities in addition to the system design of the previous existing bicycle that we have already shown. And as a main requirement is to maintain the similarity, or maintain as much as possible a similar hardware, not to say the same, but a similar hardware and a similar software of the existing bicycle. And we want to investigate if this applies on the e-scooter or not. So from here we will jump to the method, and with my colleague Linus.
Right, so one of the first considerations was picking a scooter to use. It's reasonable that it should represent what's most commonly seen in traffic. You know, what's popular, what do people actually ride? But we also wanted something that was practical, that was easy to work on, easy to disassemble, doesn't use lockdown hardware, is filled with epoxy or anything like that. So looking at what's common, rentable scooters are everywhere, different brands, but they all look about the same. We actually got in touch with all of these brands, and I think one replied. And
yes.
It was basically a thank you for your interest. Nobody else even replied to our emails. So that's out. Xiaomi and Ninebot, if you look at sort of the market of what's available, 8 out of the top 10 most popular e-scooters sold in Sweden are made by Xiaomi, so appears to be popular. One of the other 10 is Ninebot, formerly Segway, which are practically owned by Xiaomi. They invested in them for a startup, so they share a lot of hardware, they're almost the same. Considerations, practically, online communities dedicated to hacking the firmware on e-scooters to unlock the speed and make them go faster. All of them recommend Xiaomi scooters. Spare parts and availability, their parts are interchangeable with Ninebot, they're sold everywhere, you can find them on eBay. Disassembly guides are available. So Xiaomi scooters seemed like the way to go. And this is the one we picked. Notably, this one isn't legal to ride on the road in Sweden anymore because it has a 300-watt motor. Doesn't matter for us, we're just testing stuff. But that also meant it was discounted and cheap. We wanted to reuse as many parts as possible. So the front hub motor and the battery, which is located in the bottom compartment, is 36 volts, which turned out to be a bit of a problem, but I don't know if we included that. This is the baseline system that we got from Chalmers, the green bike. This is the ugly gray box that was mounted in the middle of the frame in one of the earlier pictures. This is the similar hardware they wanted us to use. If you think it looks like a bit of a mess, I agree. but this is what we were told to follow. Motor, like I said, we reused it. It's a 300 watt brushless DC motor, has Hall effect sensors for RPM, nothing special. To control it, following on from previous iterations, we used this lovely speed controller here, VESC. It's an open source project by a guy called Benjamin Vetter, not the guy from Pearl Jam. And it's really versatile, and you can communicate with most anything you want to use. It has a wonderful tool that you can configure it with via USB. It's awesome. Steering is done using a geared DC motor because it has to have a lot of torque to overcome the forces when it leans to countersteer. With an encoder for accurate position, so you can actually know where it's steering, and to control it all, a servo controller by a company called Maxon, which again, really versatile and configurable via USB. From the baseline systems from Chalmers, we got a power supply board and a breakout board for the Mario, which is the brain of the whole thing, which they were kind enough to provide. Although, as it turned out, the breakout board was the wrong board version, so it didn't actually work properly. Thanks. This is the main control. This is how the steering is controlled. This is how the whole system really is based. You have sensor data coming in, and then you use a PID to correct for it. We were recommended to use a system with an inner and an outer loop. What this really does is it runs multiple iterations to try to correct for every new sensor value that it gets. The outer loop updates slower. This was to be simulated, so we modeled the scooter accurately with accurate dimensions and weights, and made a simulation using Simulink and MATLAB, which we didn't find any more interesting pictures of in this wonderful block diagram until later. You'll see them now. And the embedded software really is just a continuation of the current implementation which we were given by the previous generations of the project. Implemented in MATLAB because we're using National Instruments hardware, so no choice there. Yeah, what did I say? Whatever. What's the result of all this? What came of it? Well, we had trouble playing the videos, but this is a lovely video of the simulation, physical simulation, which, do we want to try to play it or skip it?
We can show it later.
We can show it later. Basically, it gets pushed to the side a bit, and we see that it maintains its balance and corrects. Wonderful. This is what it looks like in more serious data than a video. Show steering angle getting nudged to the side, and the roll angle getting pushed to the side, and it steers to correct. This is using a single PID. This is using the double PID. This oscillates more, but I'm not sure what.
The result with one PID are better now, but we have to see the values now.
Yeah, the result with one PID is better now, but these are results from simulations, not real-life testing. We'll get to that. And this is what happens when it doesn't work. The roll angle goes right off to 90 degrees because it's fallen over. And now, this we do want to see.
This is the result. We can show it later also if you want, but now.
That's the whole point.
This is the IMU.
That in its hand is the IMU, the sensor. It senses acceleration, gravity, etc. And when it leans to the left and to the right, the steering counteracts. That's all we got so far. We still have a week of implementation. We were hoping this would be on Friday, not Monday.
To conclude. So back to the conclusion, where actually there were some challenges that we faced, including some lack of documentation, where there are plenty of variables that or parameters, let me say, that we didn't find the origin of these parameters, but we had reverse engineering in order to find most of the variables. There are until now a lot to test, to verify, to validate, but we hope that we will have enough time during the next week. And as a future work, actually validation and verification of the system on the e-scooter is still ongoing, and perhaps with the future generations there will be a lot to test and to validate. Also, an extra light weighted or an extra mass that should be implemented or placed on top of the scooter will help verify what are the different values of the mass of the mass of the scooter should apply. Is there a limit or not? And also, whenever we increase the speed of the scooter, there will be a change to have multiple variations of the pit values. So actually, when my friend showed the visualization of one pit or two pits, there are plenty of combinations. We are trying to find the optimal combinations until now. Maybe it will take a long time, and the algorithm will be very heavy, let's say. But we want to see if the pit values will apply or how the pit values will change when the speed will change. Until here, we reach the end of our presentation. Thank you very much for your listening, and feel free to ask your questions. Thank you.